Coming up on This Week in Radio Tech, we're going to raise the level of conversation here with John Kean and Dave Hershberger talking about an interesting study that they made and some conclusions and comments about it. It has to do with the amount of noise in the AM band and reception of AM signals in urban areas. Some of the results were a little bit surprising. So we're going to check it all out with John and Dave next on TWiRT.
This Week in Radio Tech is brought to you by Broadcasters General Store with outstanding service, savings, and support. Online at bgs.cc. By Broadcast Bionics with the Bionics Studio, including talk show control, social media, and visual radio. Broadcast Bionics brings exceptional audience engagement to radio and TV. By Air, featuring Playout One radio automation software, comprehensive streaming solutions, website content management, and social media tools for maximum listener engagement on the web at AIIR.com. By Angry Audio. Audio problems disappear when you get angry at angryaudio.com. And by Max Connect Wireless, prioritized high-speed internet service designed for transmitter sites and remote broadcasts.
Hey, welcome into This Week in Radio Tech, the show where we talk about everything from the microphone to that light bulb at the top of the tower. Hello, I'm Kirk Harnack here in Nashville, Tennessee, my home office. And we've had snow here in Nashville. It is cold. In fact, the thermometer, it's 19 degrees at the Southern Command of Telos Alliance here where I'm sitting right now. And we have a couple inches of snow on the ground. A rather interesting thing happened. Yesterday, we had a fresh pack of snow and some ice on the driveway. And where I live, there are actually, there's a kind of a shared driveway, and there's 5 houses. And my neighbor, who's fairly new to the neighbor up the hill from me, thought he would attempt going down the steep shared driveway, and didn't work out so well for him. He ended up spinning around backwards, sliding backwards across my property, across my driveway, missed a tree by, I think he scraped the side of his Mercedes on the tree, and then went over some bushes into the neighbor's yard and came within millimeters of dumping the whole car over. Let's see. I'm not going to tell you his name. I'm not going to make fun of him. He was shocked and surprised. And let's see if we can get the picture up here. Come on now. There we go. Come on now. I just took this picture today. They were getting ready to pull his car out, but there's the guy's car, and the wheel is actually in the stairwell of my neighbor's retention wall. Yeah, so and he went backwards to there. That had to be scary. So that's what we're enjoying here in Nashville, where nobody knows how to drive in snow and ice. That's my story. I'm sticking to it. I'm here in the Telos Alliance studio. Chris Tarr is off this week, but we have 2 amazing guests with us, and I'm really excited about this show. Let's jump right into one of our guests. It's John Kean, center stage. John, how you doing? Good to see you.
Hi. Nice to see you again, Kirk.
John, you are working with the folks at Cavell and Mertz, is that right?
Still am, since I retired from National Public Radio in 2016.
Mm-hmm. And we're gonna get to the reason why you're here in just a minute. Let's introduce our other guest, David Hershberger. Dave, it's good to see you. How are you, sir?
Okay, good to see you too, Kirk.
You warned us that you might have some bandwidth difficulty from where you are. You look great. That's amazing. What you're paying the right people.
Well, thanks. Yeah, I'm on a fairly limited bandwidth because I'm out here in Tahoe National Forest, and our uplink speed is limited to 2 megabits. But just looking at the meters on the computer, I'm only using about 600 kilobits right now for this video. So it's working out okay.
Well, that's about the best looking 600 kilobits I've ever seen. So that's great. John and Dave are with us today to, we'll tell you what, I'm going to let John tell you. John, I invited you here because I read something that you did, a project that you did. And you said, well, we got to involve Dave Hershberger as well. So John, if you would take just a minute and tell me, why are we meeting today?
Sure. Thanks. Well, this is a project that, came out of the National Radio Systems Committee's AM Improvement Working Group. And since I joined it in, I think it was 2019, there was a lot of discussion about the noise in the AM band. a lot of woeful discussion, and that included on the roadway, which, as you know, is these days the majority of AM listening. It's in car on the road. And I said, I don't think it's so bad on the road. And they kind of went, "Oh, okay." And I said, "Well, maybe we should do a study on that." And of course, they said, "Oh, you want to do a study? Great." And that took a few years, but it grew into this project, which I carried out in 2023. And Dave Hershberger, who's on this chat, was a great help in scheming the ideas for the technical measurements. The point here was to measure RF environmental noise in the AM band, really answer the question, do we have very much noise in the AM band that would degrade reception? And along with that, we also measured AM signals. I can give you more detail on that later, but what we really wanted to find out is how good or bad is AM reception? That was the point of the study.
And have some numbers to justify one's feelings, because if you don't notice
Right.
it, you don't know. Well, with FM or digital, you don't know how close to the cliff you are. With AM, we hear that in the background. But your experience, John, as you mentioned, was that, well, I don't really hear a lot of noise on the AM band in the car on the highway, right?
That's right. And so that's a good point. And AM reception is more susceptible to this degradation from noise. So that was what we carried out. And we learned, I'll just give away the point that we actually learned that noise wasn't bad in the AM band and in some surprising areas, as we'll get into a bit later. We also learned that signal levels from stations are not what they're always predicted to be. And that was that. And I'll show you a pretty interesting slide toward the end that will illustrate that. So all around, it was a very productive study. And
good deal. I'm excited to hear about that and to hear from Dave Hershberger in just a moment. Right now, we're going to take just 1 minute and let you hear from a good friend of mine and someone that I've actually given a lot of money to because I'm a customer of Playout One and the folks at AIR, AIIR, and they not only make the Playout One automation software for broadcasters, but they do a lot of other services that help broadcasters in the social media area. So here's Ricky Lee to tell you about it. Hey, it's Kirk Harnack, and I'm here with Ricky Lee, the CEO of AIR. Ricky, you guys make a fantastic automation system, but streaming is a really big deal. Tell me about streaming with AIR.
It really is. We've got a beautiful streaming platform with an incredible dashboard with fantastic analytics. And you can buy it for just $20 a month. All you can eat. No limits on bandwidth or bit rates. And you can also record shows as well. So if you like to deliver on-demand content for $20 a month, you can stream and deliver that on-demand content to an RSS feed that can feed your radio player, your mobile apps, or a podcast that people can download and enjoy.
Now, $20 a month, that must be for just some slow MP3, right?
No, MP3, AAC, and we also now support HLS, which is big in the industry right now.
Wow, that's pretty amazing. How do I start to explore or find out more about streaming through AIR?
You go to air.com, AIIR.com/streaming, and from there, with a credit card, you can sign up and get started.
Lots to find out about at air.com, AIIR.com. And I really appreciate Ricky and the whole AIR group being sponsors here on This Week in Radio Tech. We'll have more interesting things from Ricky in the weeks to come. All right. It is Kirk Harnack on TWiRT, along with John Kean and Dave Hershberger. All right. John, you and Dave, why don't you both together kind of describe how this, you've started, how this got started when you said, okay, we're going to do a study. What were some of the decisions to be made? How are you surely you got together and said, how do you want to execute this? What would be the most reasonable way to gather data that's meaningful?
That's exactly the case. And maybe we could bring up that slide number 2 with the
Oh,
diagram, and that'll show you what Dave and I talked about as an approach to this. There we are. And what you see in blue down there is the heart of this. That is the receiver, which happens to be a software-defined receiver. Dave, I think you have one of the RSPDX receivers made by SDR Play as well as me, right?
Yes, I do. And here's mine. This is the receiver that was used, one receiver like this. It wasn't this particular receiver. This was mine. John also has one, and John's receiver was the one that was used for the testing. But it's very versatile. It goes up to 2 gigahertz. And the nicest thing about it for us is that it can record the entire AM broadcast band at once. And so we don't have to tune to a particular station or choose the stations we want to monitor ahead of time. We just record the entire AM broadcast band. And in fact, we chose the stations to monitor after the fact based on what the reception quality was like. So that's the little black box, and it works very well. And this is an improved version of the...
I found the SDR Plus software, but what is the brand of, how is the box obtained? I see the software online.
Yeah.
It's a British company. Go ahead, Dave.
Yeah, it's a British company, and the name of the company is our SDR Play, I believe. And the U.S. distributor for these receivers is Ham Radio Outlet, HRO.com. hamradiooutlet.com is the website. Yeah. And this one lists for about $250, but, over the holiday times, you can see it discounted for quite a bit less, like $150, $175 or so. So
yeah, probably all of us are familiar with... Sorry, Dave. I think I stepped on you.
Oh, yeah, we have a time delay here. And so it's an improved version of this earlier receiver. This is the RSP-1A, and this is pretty popular too. But the RSPDX has improved dynamic range, particularly at lower frequencies, including the AM broadcast band. So this was the one to use for the AM study.
Gotcha. Okay.
So,
over.
Think of, probably all of us are very familiar with spectrum analyzers. So think of a spectrum analyzer, but as you saw there, it has no display. It is just a little black box that hooks to a personal computer. And its advantage is that it can, as Dave said, can capture and digitize the entire AM band, in fact, about 2 megahertz of bandwidth continuously in, I believe it's 14-bit depth. So it is a kind of a super spectrum analyzer, and it allows us to save all of that data to the computer and then later play it back and even analyze it. We can even play back audio from any given frequency. In other words, we can make it like a radio that is playing back in the past. And so it gave us a great deal of data to work with. Some of the other important parts of the study is you'll notice a little monopole antenna in the upper left corner connected to a box. That is on the roof of the measurement vehicle. And that is an E-field antenna. In other words, it measures the electric field. Those of you who've worked in AM measurement may have gone out in the field and had to do measurements of field strength from the transmitter site at relatively close distances to ensure that the antenna system is radiating properly. That is an H-field antenna that you use on those meters like the Potomac Instruments FIM 41. In this case, it's an electric field antenna, and that is important because that's the type of antenna that most cars use. And thanks for putting the picture up. As you see here, that's the antenna on the roof of the vehicle, that little white box, and that then feeds into the car. And that is connected through a switching system to the software-defined receiver. Also in that diagram, and we don't have to go back to it, there's a little reference oscillator which put a pilot tone on the SDR play file, which gave us a fixed level reference, which was important to ensure that later we could play everything back and trust the values, the field strength values we were measuring. So in that photo, did you have a question there, Kirk?
No, I think that was pretty smart to have a reference. You say tone, was it actually a reference carrier somewhere in,
it was an
or near the AM
unmodulated
band?
carrier at
And
I think it was like 1720 kilohertz, or no, 1620, I think, Dave. 1620 kilohertz.
No, it was 1715.
Oh, okay. I was closer the first time. And that just sat there providing a fixed reference, which was important. So in that photo of the vehicle, you'll see a fellow standing behind the car. He's not trying to take a picture of the car or break in. That is actually Tom King, well known from Kintronic Labs. And Tom is holding up his FIM 41, and he's taking a field strength measurement on an AM station. We did that on several different stations in order to calibrate the roof-mounted E-field antenna to the H-field meter. So thanks to Tom for doing that. Tom also drove all the way from Tennessee, bless his heart, to drive his car. He just insisted on helping out. So I want to recognize him for his help and his support for the project and selling it to the working group. And
good deal.
Awesome. We'll move on to the next slide here, the map. And you can see the route we used to collect the measurements. We started over to the west in that center left side of the picture near Germantown, Maryland, and you see a dark green line. That was marked as the rural part of the route. We were generally far from buildings and gave us an environment that I classified as rural. We then turned east on that lighter green area, which I called rural suburban. So the idea here was to capture a variety of environments all the way to the east and through one of the biggest cities in the country, downtown Baltimore, Maryland, which has some skyscrapers. And that gave us an opportunity to not only measure noise levels in different environments, but also what happens to the field strengths of the three stations that we measured. You can see those three stations with little red dots next to their call signs. So you see at the top WCBM and WBAL, and down at the bottom is it says WTOP. That's curious. Should be WFED, sorry. And that's at 1500 kilohertz. These are all 50 kilowatt clear channel stations. And those were chosen to cover the low part of the band. WCBM is at 680 kilohertz, WBAL at 1090, and then WFED at 1500. And we picked the route in part to stay far enough from these stations to avoid any overloading from these stations on the measurement system. And you'll see why in a bit here. We can move to the next slide. Thank you. And here's the same route, now in dark red, along with field strengths of those stations. And they're color-coded according to the colors of the call signs. So WBAL, for example, is in gray, wherever you see the gray contours, like the 5 and 10 millivolt per meter contours, that's its contour. WCBM is in green and is kind of similar to WBAL. in size, but a little different in shape. And then finally, WFED, I see I got the call letter right there, has red contours and is coming from the south, just north of Washington, D.C. So that gives you an idea of the signals that we were measuring. So we measured low, medium, and high parts of the bands from these stations for field strength, and we also measured the noise level on adjacent frequencies very close to each of these stations. And we picked those channels, what I call the quiet channels, to be unoccupied by any stations in the region during the daytime. And that gave us this so-called quiet channel to measure the RF environmental noise as we drove along this route. Let's see, we can go on to the next slide and see a chart of what the measurement looks like on the left. That's from Germantown, where we started, up to Mount Airy, and where you see kind of a knot in the drive route where we got off and turned eastbound. So in the green on that chart on the left, you can see the field strength of WBAL. That's on about a 2 millivolt scale. Actually, it's 4 millivolts at the very top. And in red at the bottom is the same scale, but for the measured noise level that we collected. In this case, it was a slightly time averaged measurement of the RMS of the field strength. So you can actually tell what the signal to noise ratio would be by looking at the difference in height between the green contour, the station signal, and that adjacent quiet channel in red. Obviously, we can't measure the noise on the same channel that's broadcasting, but they were so close that we could treat them that way. I added one of a number of maps on the report, which is about 60 pages on the right. In this case, I took the same route and overlaid it on a map along with a color coding according to the field strength. So if you look in that map in its upper left, you can see a little legend with different color shadings. It's probably as small on your screen as it is on mine, but anyway, it gives us a way of seeing at a glance what the field strengths were doing along the route. And there's a good reason for bringing this up, which we'll see in, I think, the last slide, which is a real knockout. So that was one of the things we used to evaluate signal coverage from these three stations. And as Dave mentioned, we were measuring all three stations plus all three quiet channels simultaneously. In the data.
I'm eager to see more of this. John, we're going to take a quick break. And when I've got a question that I'd like maybe you to answer and hold people through the break with bated breath, like me, because I'm curious about how broadband this noise was. I know you measured at least 3 different spots, but of course you have the data for more spots than that across the band. I'm curious as to, was the noise generally peaky in terms of frequency, or was it more broadly spread across the AM band? But we'll find your answer to that. And maybe Dave can chime in on that in just a minute. It's This Week in Radio Tech. I'm really excited to have these two super smart guys, Dave Hershberger and also John Kean, with us talking about actual measurements of noise in the AM band. And is it as bad as we think? Is it worse than we think? What suppositions do we as engineers have about where noise might be bad? And does that correlate with the data that they found? We'll have those answers and more coming up. Our show is brought to you in part by our friends at a company that'll just make your station sound better, work better, get on social media better, really better engagement with your audience. And that's Broadcast Bionics. Check it out.
Welcome to the Bionic Studio, The Bionic Studio brings all audience interaction to the fingertips of a production team in radio, TV, and podcast. Our workflow-led system is working 24/7 around the world for small broadcasters and national and international networks. Our telephony module, Bionic Talk Show, allows cost-effective centralization, remote operation, scalability, and resilience across an entire network of stations, but at the same time is used in single-studio self-op environments. Social media curation and activity is now considered a broadcast-critical part of programming. Bionic Social means the studio isn't overwhelmed with a wall of interaction from an ever-growing number of social platforms. We combine SMS, MMS, and email, together with a speech-to-text service for listeners using smart speakers. We enable studio teams to curate, filter, and display all platforms in one place, and post text, images, and video content to multiple platforms in one operation. Effortless collection of video content with Bionic Director has helped position some of the world's most successful stations as leaders in viral content, generating appointments to listen and free marketing via retweets and shares. Bionic Contest enables end-to-end tracking of on-air competitions, live reads, and prizes. These could be on-air contests, automated SMS entry, or online. Anywhere, and Skype TX for Radio brings high-quality audio and video contribution into the studio with ease. No need for dedicated PCs to run different applications. Everything is controlled within the Bionic Studio UI, and incoming connections are visible to users along with all other platforms. Our codec integration enables connection, algorithm configuration, and directory to a wide range of IP and ISDN codecs. The Bionic Studio, a unique suite of products designed to enable your talent to work smarter.
You know, in addition to the Bionic Studio, Broadcast Bionics also has the Virtual Rack, which is an amazing piece of gear and software that lets you virtualize a lot of your broadcast functionality. So we'll check that out in the coming week. I'm Kirk Harnack. It's This Week in Radio Tech, our 736th episode. Dave Hershberger is here from a secret location off in the in the woods in National Park. And John Kean is here as well. So glad to have you both. Thank you both for agreeing to be on the show. It was about a month ago that I contacted you and we set a date, and I'm so glad to hear. So John's taking, yeah, let me see if you can answer this question. Noise, did it tend to be across the AM band or peaky frequency wise?
As a matter of fact, that was part of our study, and we have a slide for that. If we go to the next one.
Okay.
And I'll give you this is all background because, of course, we really haven't discussed the findings yet, but we'll be getting to that right away. So if you look at that slide in the lower right with the blue lines, that's a measurement that was made in a populous area west of downtown Baltimore, and shows the three channels that we were the so-called quiet channels on which we were measuring noise. And an interesting thing happened there. You'll notice that they don't produce noise over time in the same way on each channel. You'll notice in the top two lines, which is the highest frequency station and the mid frequency, that there's a burst a short while in, but you don't see that evident on the bottom channel. And then later on, you'll notice that in the middle line there's that fuzzy buildup, but it doesn't appear on the other two channels. So one of the things we did learn from the study is that noise does not track uniformly across the AM band. You may be tuned to a station on the lower end and hear noise that somebody in a car right next to you tuned to a higher channel frequency doesn't hear. So to answer your question, Kirk, the noise isn't necessarily constant across the band. In this case, we saw that burst at the beginning covered more than half the AM band, but left off one section of it. So that is, it does vary by time and by location. That
Interesting.
help you out
Yeah.
with the answer.
I want to make sure Dave is on more of a delay. Dave, I want to make sure you get a chance to chime in if there's something that you have to say. So right now's your chance before we go on to the next station that you measured.
Yeah. Okay. Yeah. John covered it very well, so I don't have anything to add what he said.
Okay.
Okay.
Good. Well, John,
But
let's move on to your next one.
all right. But Dave was certainly a great brain to confer with in devising this. So he gets a lot of credit for helping. Now, going back to this slide again, we have another one of those field strengths over time in the green line. This happens to be WCBM, which is the lower frequency station, and its neighboring quiet channel in red at the bottom. You'll notice, though, the vertical scale has changed. It goes as high as 100 millivolts per meter. That's a walloping amount of AM signal.
It
as
is.
we were approaching Catonsville, which is a suburban community west of Baltimore. And as we were approaching about 10 miles distant from WCBM, its field strength momentarily reached 100 millivolts per meter. That is a lot of signal. There was also a bit of noise partway along, and that's probably because we had entered a suburban and partly commercial area, and I'll bet you that peak was something like an overhead power line or a noisy traffic signal. But by and large, that noise level was not really very high. And as you can see, that baseline remained about the same as in the rural area. So that was an interesting finding. That tells us that noise levels are generally low even in these areas, this suburban quasi-urban area, and they're brief in duration. Now, the two little graphs at the top are based on more of our data processing. And this was to understand not just the time averaged RMS noise level that you see in red on the graph, that those blue vertical lines are a frequency of occurrence distribution, telling us about very brief signals of noise and how often they occurred over this route segment from Ellicott City to Catonsville. And you'll notice that the distribution of the 555 kilohertz quiet channel chart extends pretty far to the right. So that's telling us that we have a lot of noise occurrences at higher peak noise levels still occurring in that lower frequency channel. Compare that to the one on the right at 1625 kilohertz. That one has peaks at lower amplitude to the right at about the same height, but they trail out sooner. That's telling us generally that the higher in frequency you go in the AM band, the lower the noise levels. And that was true of both RMS noise levels as well as peak noise levels. So
is that what your gut would have told you before you got these numbers? Would you have thought that?
Yeah, to some extent, I would have expected noise levels to be lower. Would you agree, Dave?
Yeah, certainly. Yeah, the lower you go, and even below, when you go below the AM broadcast band, the noise continues to go up. At least the atmospheric noise. And when you get down to VLF, it's really bad.
Right. So the higher in the AM band you go, generally the lower the noise floor and the lower the occurrences of peak noise. But the trade-off is that signal propagation, ground waves at medium wave aren't as efficient as at the lower end of the band. So it all kind of works out as a trade-off. You get more signal coverage per watt at the lower end of the band, but you get more noise. So no one really wins out on that too well, depending on frequency. Let's go to the next slide, please. And now we've moved farther east, and we're just in the area west of downtown Baltimore. So this is medium rise territory. Most of the buildings are 2 stories. And we found the noise level, in this case, again for WCBM at 5, and its noise channel at 555 kilohertz, to be quite low. But look at that big spike over to the right. Well, there's a photo of what the culprit is here. There is a light rail system on H Street in Baltimore, in the crossing West Mulberry Street. And when we passed under that, we got a huge spike of noise. And that was the overhead line, the catenary, that supplies power to those light rail cars. But again, it was a fairly brief occurrence, and all the rest of the noise is remarkably low here. In fact, it looks even lower than we saw in the suburban area. The field strength for WCBM remained pretty high. You can see briefly again it peaked to 100 millivolts per meter. That was an elevated part of the roadway, and we did find from the measurements that when you got on elevated roadways, AM field strengths rose. If you got into more obscured areas, the field strength dropped. And in fact, that steep drop you see in the green, in the middle of the green chart, is where we drove through an underpass. So you can see that clobbered the signal as you would expect. And let's see, let's go on to the next slide. And this is where we really get some of the payoff from these measurements. If you look at the chart on the left, we're still in a 100 millivolt per meter vertical scale, but the field strengths in this area were very, very low. We're looking at field strengths of maybe around a couple of millivolts per meter, dropping to below a millivolt per meter. This is on the part of the route in the map you see to the right, where we were driving east and we turned the corner from Mulberry Street onto St. Paul Street and headed south. At that point, we were heading toward the downtown area with big skyscraper buildings in Baltimore. This was part of the route that I chose specifically to find out what happens to AM field strengths. Now, this is where the color coding really can help you out. You'll notice that the field strengths are pretty decent before we turn the corner off of Mulberry Street. And as soon as we go around the corner a few hundred feet, it begins dropping rapidly and changing from green to yellow and then into red. Red, if you could read the legend, which is practically invisible, means that red is under 1 millivolt per meter. And that's borne out by the field strengths we see toward the middle of the chart to the left. That is one of the, I think, important takeaways from this study, that you can have huge field strengths a little to the west, occasionally reaching as high as 100 millivolts per meter, and you go less than a mile into downtown and the field strengths plummet to 1% of those fields. And that is a clear indication that building clutter, built up areas, have a profound effect on AM signal strengths. And let's see, I'm going to move my little camera view here. This chart doesn't show the noise levels, unfortunately.
Yeah.
But
Yeah.
what I can tell you is definitely the noise levels in Baltimore, in West Baltimore and in downtown Baltimore, were generally no worse than they were in the suburban areas and even in the rural areas. I expected the noise to just keep climbing as we approached these built-up areas, and they did not. What we did find was that the field strengths of all three stations fell into the garbage in downtown Baltimore. And then as soon as we got down to the corner at the bottom of that map and headed west again toward Camden Yards, you can see the ballpark and the diamond right there. Yeah. Field strengths bounced right back up as we got out of the shadow of that high-rise clutter. So what we learned was that noise levels in populous areas and built-up areas generally doesn't increase. The data shows that what we hear is a severe drop in the field strength. And if there's not much signal left, any noise that might be there is more bothersome on our AM radios. So that was a major takeaway from this study. We can go to the last slide, which has sort of the summary items and covers some of the things that we were just talking about. One is that the field strengths that we measured did not follow those ground wave field strength maps I was showing earlier very well. In places, they deviated by a significant amount, which is not something that we generally expect. We draw these beautiful contour maps of AM stations based on the M3 conductivity data, and we get these nice rounded contours that go large distances. And what we learned was that isn't necessarily so. Due to various reasons like local variation in ground conductivity, that's not what the M3 data shows. Could also be terrain data, terrain effects, and then finally building clutter. Field strengths are sometimes quite a ways from what the map shows, especially in the built-up areas. So building clutter is something that really is ignored in AM maps and should be probably added if we wanted to really know what AM stations coverage looked like. That would be a big benefit. We found that yes.
I can tell you, I'm definitely going to have some questions, and I'm sure you or Dave can add to these. We're going to take a quick break, but I'm going to ask you to think about. I know you used this somewhat specialized antenna because you could control it. You knew its characteristics to a good degree, and you could calibrate things. I'm curious about if you think that people's reception results might be different just with the standard shark fin antenna that so many cars have these days. I've got a couple of older cars and they've got, vertical whips, but most of them today don't. And I'm also like to hear your comments about the similarities apparently between building clutter and going through a steel bridge. Stephen Wright for years had this joke where he would say, I have a friend who's a disc jockey. Whenever we go under a bridge, you can't hear what he's saying. So we're all used to that. You go through a steel structure. I'd like to hear about that, and a lot of your other thoughts about noise, and maybe noise versus in the home versus out on the highway. I've got a couple observations of my own that I'd like to pass by you. So it's This Week in Radio Tech. Dave Hershberger and John Kean are our guests I'm Kirk Harnack, and our show is brought to you in part by our friends at Angry Audio. As they say, don't get mad, get angry, and your problems will get solved. Angry Audio has this audio console that they'd like me to tell you about. It's an analog audio console, but man, I don't know if you've seen one quite this nice before. This is an 8-fader console, 8-fader analog console, and then the 2 extra faders are for your monitor volume and your headphone volume. This thing is absolutely built. I got a sneak peek at this thing literally a year and a half ago, and Catfish, Mike Dosh, the fellow who owns Angry Audio, asked me to open it up, take it apart, and have a look inside. This is heavy duty. It is so well built. This is going to last longer. Well, this is going to last longer than your radio career, I'm telling you that. You'll retire before you wear this thing out. The buttons are all avionics grade buttons. They are high quality. The faders are also they're the best you can buy. And this thing is heavy. It's steel. It's a steel case, and it just feels good. It's not going anywhere on the desk. No, it's just going to sit right there and let you work it. The inputs on the back are XLR connectors for the mics and Studio Hub RJ45 connectors for the line inputs and outputs. It has, of course, a mix-minus bus for your telephone hybrid, a mix-minus bus for your codec. The mic preamps are just super quiet. Mike Dosh knows how to design high-quality audio electronics. He's been doing it for years and years, and starting his career with audio consoles at PRE, and you know how good those things were. So check it out at angryaudio.com. This Week in Radio Tech is also brought to you by Max Connect, and they have a device that, I'm telling you need. Max Connect makes this box called the U.192. Now, what is it? Well, more and more radio stations are implementing a software-based FM audio processor for their FM and also maybe for their HD1. And these are pretty cool, like Omnia SST, Stereo Tool, Breakaway One. These run typically in a Windows environment. And the one problem is there's no computer in the world that's got a BNC 192 kilohertz sampled output. Yeah, some audio boards may claim 192 kilohertz, but let me tell you, what you need for broadcast is ruler flat and phase linear across the whole spectrum up to 192 kilohertz. In other words, that MPX signal is a little bit fragile, and you want it to be treated exactly right. Well, that's what the U192 does. And it's bidirectional. Now, it only puts out on the composite outputs, but if you need to bring your analog audio in or your AES-EBU audio in this way, you can do it. It's USB connected to your computer that is that's running your FM software. Again, whether that's Omnia SST, Stereo Tool, Breakaway One of those. And so you can get audio in at high quality. You can also get the multiplex composite signal out super high quality with the U.192 USB interface. This is the brainchild of Josh Bone over at Max Connect. And of course, he tapped Mike Dosh over at Angry Audio to design and build it. So you know the quality is there. It's heavy duty. It's got a great case, steel case. And it has the few little options that you need to select what's going on, and it's rock solid. Check it out if you would at Max Connect, MAXXKONNECT. We'll have a link in the show notes to the U.192. Whether you got your transmitter is local, it's close to your processor, or maybe you've got a composite STL link, whether it's an analog or a digital composite, use this to feed that. Or to feed your exciter if it's right there on premises. Thanks a lot, Angry Audio and Max Connect, for sponsoring This Week in Radio Tech. Check those things out. I'm Kirk Harnack. We've got about 15 more minutes left in the show. So John Kean and Dave Hershberger are with us. John, did you have we were on the last slide. I don't know if we got done with that, but I wonder if you might address my question about shark fin antenna. Do you think you'd get similar signal noise results with that kind of preamplified antenna that comes on most cars these days?
Well, yes, generally you would. Of course, radio performance can vary from cars to cars and from our SDR receiver. But no, I would say when you go back and you look at the data, which we didn't drill down on here, of course, you see quite decent signal to noise ratios, you might say, in the RF domain. And that means they would be receivable on shark fin antennas as well. I would say those shark fin antennas do have less gain than the antenna we're using. I don't think anyone has characterized it. It's probably known to car manufacturers, but they're not going to tell us. So I would say yes, you'd get better reception on, say, your car, Kirk, and mine, which have the old fender-mounted vertical antenna, which are still great for AM. In fact, they're great for FM as well. But they'll work. It's the noise that really starts to degrade AM reception, and that's probably one of the important takeaways from our talk here, is that we found and demonstrated that field strengths can fall substantially. AM field strengths can fall substantially in built-up areas. Now, you mentioned about driving under an overpass or through a tunnel, and of course, we all know that's going to knock out AM. What I think we're generally not expecting, and I really wasn't, was if you're driving through that part of West Baltimore, which is the low-rise commercial area that's rather old. Buildings are often only 2 stories high, with an occasional slightly taller building. And you don't think the AM field strengths are going to be affected, but as soon as you get into those built-up areas, you see that AM field strength begin falling off in the measurements. And the taller the buildings get, the more the field strengths drop. So what we have with all AM stations that have transmitter sites located out in the suburbs, or maybe even out in rural areas, WBAL and WCBM are definitely out in rural areas, 10 to 12 miles northwest of downtown Baltimore. Those field strengths are not what you would expect. And that has as I say, a profound effect on the AM reception, regardless of how good your car antenna is. And that may lead us to a bit of talk here about the last thing that we could get to, and that is, because we know that AM signals are so significantly affected by built-up areas, AM stations are losing listeners. They can't reach in the most populous areas of their market when their transmitter site is maybe 10 miles away. And you think that you're going to have a great signal because you look at the coverage maps and it says, oh, you should be getting 25 millivolts per meter here. And it turns out it's below 1. Well, that was an important takeaway from this study, and it really surprised me in the amount of effect it had. Would you agree, Dave?
Yeah, and AM radio has been around for a long time, and you and I had some conversations about why didn't people back in the 1930s know this? And the answer that we came up with was, well, they didn't have SDR receivers. They couldn't record the entire AM broadcast band. And what are they going to do? Go out with a strip chart recorder and listen to just one station? And they probably could have done it that way, but nobody did. And, now that we're able to make these measurements and come to some of these interesting conclusions.
True. But in my view, I think many of the AM broadcasters knew this. And let me ask Kirk if your control room is able to put up the second page of that report.
Yeah, that was this
one right
there. You
there.
go.
Yeah. Great. The reason this is important is that this is the next project in the AM working group at the NRSC, and if you scroll the page up a bit so you can see the photograph, other direction. There we go. that's a photograph, I believe, from 1927, 27 or 28, a century ago, effectively, of WBZ AM in Boston. They knew that they had coverage problems in the city of Boston from their primary transmitter site as soon as they went on the air in the early 20s. And what did they do? They built a single frequency network so they could create a second transmitter that repeated the exact signal transmitted by the primary transmitter. And that's a photograph of the single frequency network transmitter. It looks pretty quaint by today's standards. You see equipment sitting on tables and lots of wood panels containing meters. But here it was a century ago. They already recognized that problem with field strengths being severely attenuated in populous areas, the built-up areas, they call them. And that's the genesis of the next project. And that document you just saw there is where we're going to do parameter measurement on AM multipath, because when you have a primary transmitter and a secondary transmitter located miles and miles apart, you have time of arrival differences based on the receiving locations in the area, as well as differences in field strength. And the question is, what is the effect of that time differential and field strength differential on receivers? And that has not been well documented for many years. We're going to be conducting measurements right here in my house. As a matter of fact, in my shop downstairs, I have a Hewlett-Packard RF channel simulator that Gary Cavell bought for me in order to create those time differentials very precisely, so we can offset times of arrival as well as change the field strengths, so we can then feed that to a receiver with real program audio and then record the results. And then after the recordings are made, we'll do a listener test, kind of a controlled listener test, to have people rate the quality of reception. And then I'll be able to put that into a matrix and use that matrix data to predict what is the multipath effect if I were to build a single frequency network booster over here and my primary transmitter is over there. And I can even then adjust the design parameters. I can move the booster location, or I can change its power or its radiation pattern to shift the multipath to areas that are less important. That's going to be our next project. And it really arose out of these findings that we need to see whether a single frequency network can help out these problems that AM has been having for a century. The nice thing about it is, back in those days, and in fact, until relatively recently, until I'd say the 21st century, AM broadcasters didn't have the technology to generate a carrier frequency on the booster transmitter that was in exact lock with the frequency of the primary transmitter. Back in those days, they came up with different schemes to try to synchronize, but it didn't work too well. The other problem they had was trying to synchronize the modulation precisely. And nowadays, we can digitize the audio, much like the technology you were talking about in your spot a few minutes ago. And once it's digitized, we can ship that digitally to an SFN booster site, decode it, and synchronize the two modulations just as we need. And we can minimize the multipath effects and be sure where they occur geographically. That was not something they could do. And so broadcasters for decades built these SFNs and had varying degrees of difficulty making them work right. Often they turned them off out of disappointment, and it was understandable. But today we have the technology to build an SFN and make it work the way we expect. That's what we're going to be doing in our next tests, so that we can design them or determine how well the designs work in any given station.
I'm looking forward
how's that
to
for a next step?
yeah. I'd love to hear the results of that. I will tell you, back, this would have been in the mid 80s. I was shipped off to Santa Fe, New Mexico to do some work, rebuilding work at a radio station. And there, was a booster in Santa Fe of a station in Albuquerque, right? And Albuquerque,
I think, is the primary, and Santa Fe is the secondary, the booster,
exactly.
Call it.
And they of course they couldn't precisely lock the two, but they did use an external frequency reference for the booster that kept it really close. Now, the benefit that they had was there was no population between Santa Fe and Albuquerque, and so in the area where they overlapped, nobody lived there. So
that was the highway between
some snakes.
Yeah. Exactly. Yeah. Kind of the middle of nowhere along the highway. Actually, the WBZ in Boston that I was showing the photo of, they came up with a very unique solution for synchronizing the carrier frequencies. They divided down the crystal oscillator of the primary station to about 19 kilohertz, I believe, and they figured out a way to transmit it over the open wire telephone lines to the booster transmitter on the other side of Boston. And then they multiplied it back up and fed it into the booster transmitter. So it was an ingenious solution. They still had the problem with synchronizing the modulation. That was, I think, tough to do. And but today we have GPS for frequency control and digitization, so we have a possibility here of this working. I hope I'll be able to come back with Dave and tell you later how a real test system works.
Speaking of Dave, is he still there? Dave, are you still in the forest? Hey, good.
Still out here
gentlemen,
in the forest.
And I'm sorry that you haven't got a word in edgewise, not too many. But guess what, Dave? Your time to shine is coming, because we're going to take our last quick commercial break, and when we come back, it's time for our tip of the week. And so, John, you've already kind of blue skied what's next. If you have if you have a tip for us or something that you'd like for broadcast engineers to be thinking about or to study up on, I'd love to hear about that. Dave, same for you. I'd love to hear if you got a tip of the week, whether or not it's exactly related to this topic. I know you have a whole career of great learning and some wisdom to share. So hang tight. We'll be right back in 2 minutes. This Week in Radio Tech is brought to you in part by Broadcasters General Store, BGS, and their partner company is Broadcast Tools. Broadcast Tools is one of the lines that BGS carries, of course, and Broadcast Tools makes a device that you're going to find very useful. More and more stations are, station clusters. And I just installed 3 of these devices, the Broadcast Tools. What's the name of this thing? I should know. I just installed 3 of them. It's the Broadcast Tools MSRP3, Multi-Station Relay Panel 3, MSRP, Multi-Station Relay Panel 3. Of course, Multi-Station Relay Panel, well, what it does is it lets you interrupt the audio on 3 radio stations in stereo at the same time and insert some other audio. Well, what would that be good for? How about EAS? So my stations in Hawaii, we've got 8 program feeds at the same time. They all have, same EAS coverage area for that matter. They're on Maui. So we use 3 of these to get a total of 9. We use 8 of the 9 interrupts for our EAS signal. You can also use the interrupt relay that's in your EAS box itself, if it has one, and most do. So that would give you, if you had one of these boxes, a total of 4. So just add 1 to however many you have through the MSRP3. This box was so easy to install. I love it. It uses the Studio Hub audio connectors on the back. So Studio Hub click in, Studio Hub click out. And I happen to use Axia X nodes to feed audio out and through these and then back into my Axia system. The signal noise is amazing. It's well over 100 dB of signal to noise ratio. And the broadcast tools is just really easy to wire in to my my Sage NDEC EAS box, and it just worked great. I was able to wire 3 of these in, probably did it, including making the custom length cables, probably did it in about an hour. So 3 of these installed in the rack on a shelf, and you can get a shelf from Broadcast Tools and wire them in and out because the connections were so easy with Cat5 cables and RJs to my my X nodes that it was just easy peasy. Love this box from Broadcast Tools. And Broadcast Tools makes so many things that'll make your life easier in building a broadcast facility, whether it's in the studio or whether it's in your rack room or even at your transmitter site. Check out solutions from Broadcast Tools, and you can get them from BGS, Broadcasters General Store, at bgs.cc. But you know how I tell you, they love getting phone calls because they're good at it. 352-622-7700. I think I've had that number memorized for 30 years now. So give them a call at 352-622-7700. Great prices, quick quotes, the fastest possible shipping, and they can tell you, when something's going to arrive. So when to be at the station to receive it and put it in. Thanks a lot, Broadcasters General Store, for sponsoring This Week in Radio Tech. All right, we just got a quick couple minutes on our last segment here, and so we're looking for a tip of the week. Who wants to go first? John, you got your mouth open. You look like you're about ready to talk.
Oh, I've been running off at the mouth here. I should let Dave make sure he doesn't have something he wants to add about our study of AM multipath.
That's a good point. Dave, go right ahead. What you got for us?
Yeah,
Your
okay.
thoughts?
Well, what I did was the post-processing of all of the wave files that were produced by the Beaver for John's work. And so my input was the output from the SDR play receiver recorder AS band. So I wrote code, or actually I should say I rewrote code that would select one particular station or one of the noise frequencies and then make measurements of what the signal strength was and also to decode the audio. And that's an outgrowth of a couple of other things that we've been doing in the NRSC AM Improvement Working Group. And what got me started was doing a co-channel simulator. And this relates to what John's proposed project is going to be for synchronized boosters. And there was talk of doing some tests to synchronize a number of AM radio stations on a particular channel, and then to go around to different receiving locations at different times of night and make recordings. And I started thinking about that and thought, well, it would probably be a whole lot easier and a lot faster to do this in software. And so I started thinking about it, and then it dawned on me it would actually be pretty simple to do this in MATLAB or in another tool called GNU Octave, which is like MATLAB, except it doesn't cost thousands of dollars. It's open source and it's completely free. So I did it in Octave, and lo and behold, we have a bunch of recordings now. And the source code is published and it's on GitHub. Anybody can go get it and run simulations of, what would it sound like on this channel if we had a desired to undesired ratio of 3 dB and what would a receiver sound like? And that led to another project that we're doing in AIWG, which is advanced receiver techniques. And what I want to do and what's in process now is making a receiver that can make decisions about what kind of demodulation technique to use and what kind of interference rejection techniques to use. And one of the examples that Mark Persons came up with is there's a situation near where he lives where two stations on, I believe, 920 and 930 are exactly the same signal strength close to his house. So he recorded those off the air with another SDR play receiver, and I wrote code that would take the output from the SDR play receiver and separate these two stations by doing single sideband reception of one, receiving the sideband only on the opposite side from the interfering signal on the adjacent channel. And guess what? You can get 10 kilohertz audio doing that, and it sounds pretty good. So we're having a lot of fun with AM stuff and the AIWG. That's about all I have.
Cool. I'll put links to that where I can in the show notes. John, you have a final thought?
Yeah. So I think you were asking, and I'll say that we shouldn't rush out and build a single frequency network for AM, even though they used to exist. We've got some research to do, but it looks very encouraging, and it could potentially recover thousands of listeners for AM stations where their signal is deeply shadowed, as we found in today's study that we were discussing. So it looks very encouraging to me, and stay tuned, as they say.
I was just thinking about your methodologies and the SDRs that you used, and thanks, Dave, for showing us that. I'll put a link to that in the show notes as well from Ham Radio Outlet. But I think we missed an opportunity politically here. You know, we've got this AM for every car bill in Congress. It should have been SDR for every car.
Yes.
Yeah.
Agreed.
That way you could pick up anything, right? Of course, you have to have an engineer, an engineer and a laptop come along with that.
Actually, it may be surprising to you. All car radios today are software-defined receivers. They use a chipset that do the digital signal processing. The thing that we also need to look into is how to improve their performance. A lot of the megaflops, as the manufacturers call it, are being used for FM, but they're not using it on the AM. And it's only because the license for that processing may cost a nickel or a dime for the manufacturer to turn it on or to put it into the chip. So they are just squeezing that little bit of money out, and they're degrading the potential performance of AM. So that's something we hope to look into here soon.
Gentlemen, we have pushed my producer, Suncast, well into overtime, so we're going to have to go. I appreciate so much both of you being with us, John Kean and also Dave Hershberger. We'll have show notes on the show and invite you back again after you look at more into this single frequency network. But we got to go. Suncast, thank you so much for your work in putting this show together and being quick with the graphics. Really appreciate you. And those of you who watch this on YouTube, be sure you hit like and subscribe. Thank you very much. Love to make you aware when we have new episodes come out, usually every week on Friday with the edited version. So thanks very much for supporting us and supporting all the advertisers. We'll see you next week on This Week in Radio Tech. Bye.